welcome to APEC Open Mic. It is Saturday, November 9th, 2024. Happy birthday, APEC. So this is our 4th anniversary. I am on site at Falcon Space. I've got a lot of our usual development team, the folks who are actually doing the work with me. And so they're going to join in. Hopefully we'll do some live experiments. We've got vacuum chambers set up. We've got 4 or 5 projects being built underway. I'm really excited about that. And that is just what's here at Falcon Space. I know a lot of the folks in our community have stuff as well, right? Like I see Curtis in the audience and other folks who are building stuff. So we have a lot of really exciting stuff. So what I'm going to do, let me see, I'm going to let everybody, I'm going to allow to unmute themselves. I'm going to remove the spotlight here. And I believe if you want to talk, it's Option Y on Windows or Alt Y on Mac to raise your hand. I'm going from memory on that, so I could be mistaken. And again, this is open mic. So, you know, if you want to jump in, as long as it's not cutting anybody off or interrupting, jump on in. So should we start with introductions, guys? You want to do that? Try and run through real quick. We've got about 20 people here. Yeah. Let me see. Let me go to Robert Francis Jr. first. Sir?
Hi, Tim. I've been working on magnet free fall experiments, and I discovered that there's like a polarity where if a dipole magnet, if it falls in the direction of South Pole to North Pole, there's no effect. But if it falls North Pole to South Pole, there's progressive acceleration. So
okay.
it's increasing.
Yeah, and if you want to share more about that today, that is totally cool. And then
Cool.
let me see. I think Curtis and Jim Woodward have some updates. And you know what, guys? I mean, again, today's kind of more mellow and relaxed. Should we skip the intros? Just kind of go right into it? Rick, what's up, sir?
I was just saying we should skip the intro.
Yeah, well, let's
we've done it so many times already. Everybody knows each other.
Yeah. Well, and one of the reasons that we did that was we're trying to build a community, right? We're trying to increase that community just so that people know each other and interact with each other and they can share, you know, and they have contacts to reach out to and all that stuff. Okay. Yeah, Michelle, did you have a question? Did you have something to say?
No,
Oh, Michelle, I'm sorry. I hit the wrong button. Okay. I'm sorry about that.
Hey, that's okay. I'm sorry I've missed the last several months worth of meetings. I've been a little ill. It's been about 2.5 months in the hospital with my pancreas and gallbladder having war.
I hope you're feeling better.
I'm slowly feeling better. But congratulations on your 4th anniversary.
Well,
I bet 4 years ago you didn't think you'd make it this far, and you have really increased your audience, and your professionalism is excellent. I'm glad to be here. I'm glad to see you're doing what you're doing. For anybody that doesn't know who I am, I'm the senior engineer for Woodward Group, and I have my own little lab that I work with. So that's it.
Yeah. Well, and Michelle, when you're feeling a little better, I'd love to have you kind of do a walkthrough on your stuff as well. So
I would love to do that. Yeah. Right now, I'm just trying to get my feet underneath me. You spend almost 3 months in the prone position. It takes a while for you to get back. I lost about 40 pounds.
Oh, wow. Wow.
So, yeah. So I'm getting back and I'm feeling a lot better. So,
well,
we have some really good things going on with the Woodward Group. Some really, really interesting data to share.
Yeah, that's wonderful. And then they're looking at, I know Jim and Curtis are working on a new vacuum chamber, right? Or a new vacuum pump. And so that's on the way as well. And so there's a lot of really exciting stuff going on right now.
And we're actually, I'm actually revamping up some of the work I'm doing. If I couldn't spend time in the lab, I actually spent a lot of time going over AI and optimizing, working with AI and evaluating the data sets that we get. And it's led to some really pretty interesting results. It made everybody happy. Let's put it that way.
So it's exciting. And I know you guys are getting amazing results. And I'm seeing other results too. So I saw a B-field Brown device in the vacuum chamber today moving in a vacuum. And so we are actually they're pumping. Mark is pumping the vacuum chamber down now, and we're going to see if he can get that to work in a hard vacuum.
That would be interesting to see.
Yeah,
I would love to see that.
surprised. I mean, what did he say it was? I think it was 10 to the -5th or 6th torr, but the remainder was they pumped it full of sulfur hexafluoride instead of air. They pumped out the air. So he was saying the equivalent vacuum was actually harder. And we had movement. There was a high voltage to Cockcroft Walton like a Jacob's ladder bridge in there powering it, and it had shorting on the resistors, and so they're swapping that out. But it was really exciting to see. And then the other thing that I'm really excited about is like the amount of teamwork that is happening, not just here, but again in our community, is really exciting, right? It's people collaborating and sharing and working together, and that's what makes this stuff work. That way if somebody gets stuck, they have other people who can help them.
Oh yeah, there's the one mind of many outweighs the one.
Yeah. Okay, well, let me see. Should we go? Do you want to go to Robert Francis Jr.? Robert, do you want to give us an update on your stuff? And then after you do, then we will just pick our next victim after that. So again, today's real mellow. I hope I'm doing okay, guys.
Everything's cool.
I just got like a 17-hour plane ride yesterday. So
Oh wow.
yeah. Well, it's thanks to layovers and delays, right?
Well, that's why we need this technology, flying cars and faster passenger aircraft. All right, let's start the slideshow. All right, updates on my dipole magnet free fall experiments. This is a slide from the original Mark 1 experiment. And basically, I was able to determine that nothing really happened with all the magnets and the controls, except for the magnet that was two attractively coupled magnets when they were moving in the direction of north to south pole. Then they had progressive acceleration increasing until the impact with ground. The takeaway from that is claims by Boyd Bushman and others that two repulsively coupled magnets fall slower than a non-magnetic control object was not observed. What was observed is the dipole magnet in free fall moving in the direction of north-south pole experiences progressive acceleration that does not stop until the object impacts the ground.
And Robert, sorry to interrupt. Were you sharing? Are you trying to share? Because it's not sharing.
Oh,
sorry about that.
No, that's
just describing it for a moment, and then.
Yeah, I had a PowerPoint.
Okay, yeah. Try hitting the share button again, and make sure that you finish. It's going to make you click a couple more times to finish that share.
Okay.
And let me apologize for interrupting you.
No.
There we go.
That's good. Okay. Is it still good?
Yeah. You want to take it from the top? It looks like it's two panes now. It looks like it's.
Oh, yeah, I guess I'm sharing it's supposed to be sharing the other screen, but dang it. I really have to learn how to use this.
Oh, here, you know what? Why don't I do this? I can, yeah. Okay. If you stop sharing.
Oh, okay. Here we go.
Perfect. There we go.
All right, cool. All right, so this is just the line chart. There. This is just the line chart from the original Mark 1, and you can see that the two attractively coupled moving in the direction of north to south, there, the yellow and the green there, those are the ones that experience progressive acceleration, while the rest of them were pretty much around gravity. And I already mentioned the takeaway. Progressive acceleration was only observed in dipole magnets moving in the direction of north to south pole, not south and north pole. And I want to say it is a Beefield-Brown effect moment. Just as Thomas Tanson Brown discovered a high voltage capacitor moves in the direction of negative to positive capacitor plate, I have discovered a dipole magnet experiences progressive acceleration when under impulse in the direction of North Pole to South Pole. To my knowledge, no one else has discovered this. Can we call it the RFJ effect? Modifications that failed since last open mic. Well, efforts to lengthen the plastic shell encasing the dipole magnet with a longer shell and a 75-degree taper on the back third, along with large fins to improve overall aerodynamics and move the center of pressure farther back. They were made in order to keep the object falling vertically, North Pole to South Pole. While it fell more vertically, these changes were not successful. Why did they fail? I believe the back end of the shell and foam encasement were too far away from the dipole magnet's field, and as such, the field did not encompass the middle to the back third of the freefall object. As a result, its inertial mass was not reduced, but its its acceleration rate was poor. Successful modifications. Minimizing shell size. The complete Mark I plastic shell was reduced in length from 120 millimeters to approximately 90 millimeters in the Mark X model. The inner diameter of the shell was reduced from 64 millimeters to 59.55 millimeters. Aerodynamic improvements. The attachment points in the bottom and top half of the shell were moved partially internal. This the holes in the bottom shell, the back end shell were tapped. The holes in the front end shell were tapped with a tap and die, and the top shell was attached to those threads with the back end shell was attached to those threads with M3 nylon machine screws. I also using a new accelerometer. The original accelerometer in the Arduino Nano 33 BLE Rev2 board was not as accurate as I would have preferred. In its place, I'm now using an Adafruit BNO055 IMU, which connects to the I2C port of the Nano. The new IMU has auto calibration and also converts the G-forces to meters per second squared, making generating the data easier as well. Here's where you get just two images from CAD. You can see the difference on the connection points where they're more inset, and I had a fillet, like a rounding over on the front of it that helped aerodynamics. The back end, they're both still like 45-degree angle. Additional modifications. Multiple taper angles are being tested. I am testing taper angles for the back end of the shell at 45, 55, 65, and 75 degrees. Normally, a longer, more moderate taper of 75 degrees would be better, but due to the limits and the magnetic field size, this is not possible. Preliminary tests to show better acceleration rates with a taper of 45 or 55 degrees compared to 65 and 75 degree tail ends. Multiple fin sizes are being tested in the 45-degree taper variants. The model with the largest fin, 10 millimeter in height and 25 millimeter in length, had the highest average acceleration rate of 11.8448 meters per second squared. The 55-degree taper with their smallest height was around smallest fin height was about 11.8395 meters per second squared. So you can see this is a line chart of the 45-degree taper with and without fins, and you can see the maroon one at the top. It's in between 11.75 and 12 meters per second squared. Like I said, 11.8 odd meters per second squared. And then you can see the 55. It's also similar performance. The 65-degree one was lower performance And I think it's just because, if you had a longer taper, then once you reach the end of the taper, it would have a similar diameter to the ones I have with the 45-degree taper. So I think that might be affecting things that way. But and then the last is a 75-degree taper, and you can see it's not the 65 and 75 aren't performing as well as the 45 and 55. So yeah, an acceleration gain of 0.75 meters per second squared between the Mark 1 and the Mark 10 models. Increased because of the reduced shell size and decreased foam within the shell. So the magnet is encompassing more, and the aerodynamic improvements also helped. Future avenues of experimentation. Higher free fall experimental trials. I have access to a drop height of approximately 20 feet. And then I can test the best performing Mark 10 shells, although I don't know how well tumbling and rotation will happen to those. I mean, if I'm lucky, a guide wire system might not be necessary if the fins and the aerodynamics can keep the object falling vertically. Another avenue of experimentation, build a guide wire system. I'll be building a small scale guide wire system about 7 feet tall that I can do in my house just as proof of concept, and using 2x4s and vertical guide wires composed of PTF coated fishing line. And the goal in the acceleration rate in the shell when it's traveling north to south pole, the entire free fall. That's what I want to have happen, because I think that'll provide the best results. But yeah, it's possible there'll be friction between the fishing line and the PTF tubing. So it's anyone's guess at this point how well that's going to work. If it does work, the 7-foot one, then I'll be building a 20-foot tall one, and to try to achieve even higher acceleration rates. And one, I think this is the last avenue of future experimentation. You use more than the current 2 magnets. I bought a total of 6 of those N42, 2-inch diameter, 1-inch thick, with a 1/4 inch internal hole neodymium magnets in order to test attractively and repulsively coupled magnet configurations. And since the repulsive ones don't really do anything, and they're just sitting in a box now, I could try stacking the magnets vertically, which will probably not increase the strength of the field very much at the front of the stack, but each magnet weighs approximately 380 grams. So such a vertically stacked arrangement should provide a similar inertial mass reduction field while also increasing the gravitational mass of the freefall object. With the inertial reduction field staying relatively the same, but gravitational mass increasing, the object should reach even greater levels of acceleration during freefall. You can check out my other work on my website, robertfrancisjr.com. The URL below that is this replicate my experiment to replicate the magnet freefall and gravitational mass experiment. My experiment replication guide is a bit of a work in progress. Basically, I just need to replace the existing .stl files for printing the 3D plastic shell from, I think it's the Mark II is on the site now. And the Autodesk Fusion 360 CAD files, which would also be the same version. I want to update those to the best performing Mark 10 version. And I should have that guide updated by the end of the week for anyone who wants to try to replicate the experiment. It's the biggest thing to do is if you already have access to a 3D printer and CNC router, you're like 90% of the way there. And then of course, if anyone can endorse me on ArcSiv, I guess in general physics, shoot me an email. I'd appreciate it to get on there. And that's it. All right. Thank you.
Awesome. Awesome.
Thank you, Tim. Thank you,
Robert,
everybody.
thank you. So, I had a couple of thoughts, if it's okay. So one of those would be, when you mentioned changing the casing, changing the taper and adding fins, I thought, you know what, that's going to cause trouble with all of your data, right? Because then you're going to have to recalibrate all of that data based on that. Have you thought about like coming up with a standard package and just saying like, it might take a little research, right, to figure out, okay, these are the standard magnets or the size I'm going to use. But like my thought would be maybe if you had a sphere, and then if you had a sphere, it would be interacting as little as possible with the atmosphere, right? It would be very known. You know what I mean? Like, because if you have fins and stuff, you're going to have atmospheric change, you know?
Yeah, the fins, I do worry about the fins causing problems. That's definitely true because when I tried that really, like I said, the one that failed, that was like a long tube and had large fins, and even though it helped it stay vertical, it just introduced too much drag and
Well, and like if you ever go to publish on this, like one thing you could push back on it, and I could be mistaken here. So I might not be talking straight, but my thought would be if you did have like a spherical chamber, then nobody could complain, right? They would say, well, it's interacting with the air, and you say, look, it's a ball from one to the next, that remains constant. So the only things that could change would be the weight and the magnetic forces, right?
I don't know.
I mean, you could do the same.
Yeah,
What you have right now is like a pill shape, and you could probably make the same case for that too. So,
yeah, I mean, I want to say Boyd Bushman supposedly used, spherical ball, but then the problem is how do we keep it moving vertically North Pole to South Pole? If it's a ball, then it would. Not saying that would work. I would just say it would probably require the a guide wire system to, keep it falling in the right direction. But yeah, that's a good idea to try for once the guide wire system is built, and I'll have to look into that and test out some different models.
yeah, yeah. Well, and again, I'm not trying to cause trouble for you. I was just floating ideas. The other one that I thought would be interesting would be just trying higher heights if you're able to find any. Like could you find something that's 100 feet, which is taller than it sounds? So
Yeah, I was
bridge.
20 feet one was going to be out my dad's second story window above the basement walkout. So, so in a way, like 3 stories. Yeah, I haven't even tried to find like a even higher level. I'd have to have like quite a bit of padding. I've used I've used the folded over mattress topper to cushion the blow when it hits the ground.
Oh, okay, yeah. So that's another issue also. Let me go to Rick. He has his hand up.
Um,
Oop, Rick. Oop,
okay.
okay.
Hello, Robert.
Hello.
I was talking to a guy who did experiments using different materials to measure the gravitational constant of Newton. And he found different elements affected the gravitational constant slightly. So my question is, did you ever try using cobalt nickel or ferrite magnets? Because I think the electron orbitals would affect the result.
Huh. No, I've only tried neodymium.
Okay. My suggestion would be try different magnets to get more experimental results.
Okay. Okay.
That's
I'll,
all.
Awesome. Okay. Well, thank you, Rick. Let me go to Henry. Henry, go for it, sir.
Um, I can see the problem with going to greater heights is the smush factor. At some point, you're going to be fracturing that Arduino board,
Mm.
as well as the case. So
yeah.
comes a point where you can't
Oh,
test
yeah.
except for destructively.
That's a good
I mean,
point.
I've done the 21. It was like the 20-foot one with there's an old beat up couch and then mattress topper folded in half, and that came away okay. But yeah, I haven't tried any higher heights. So
And going back to Tim's suggestion of doing a sphere, one way you could ignore tumbling is a very small gyro. That way, it's going to be forced to stay in one orientation.
Huh. I'll have to look at that.
It gets rid of having to screw around with fins and everything else. You just got a ball and a gyro. It stays in one position. You drop it, you're done.
Yeah, that's a good point.
Cool. Yeah, definitely.
And with lithium-ion batteries packing a hell of a wallop power-wise, a couple of rechargeable batteries, and you have plenty of power to spin the sucker up and, repeated experiments. And with a sphere, you could do, I think, better bracing for strength versus, your kind of pill-shaped
yeah.
plastic.
Yeah.
Okay. Oh, yeah.
Awesome. Well, Henry,
That's
thank
weird.
you. Let me go to Mikolaj.
I have a question for Robert. Have you done like a thorough analysis of the interaction of your magnets with the Earth's magnetic fields? Because you mentioned the other day that, okay, who cares because the magnets are strong. It doesn't really matter. One of the magnets may be the weakest magnet on the planet, and the other magnet may be the strongest. And the interaction is the multiplication of them plus the distance and stuff like that. So I would suggest before you invest in on all those, heights and stuff like that, please do a thorough analysis of the interaction of the Earth's magnetic field with your magnets. That's my 2 cents.
That would be over my head. Right now, I'm not saying that I don't know. I mean, like I said, I tried the repulsively coupled ones, and they didn't really materialize any results. And the ones moving in south to north direction didn't really materialize or any results. They stayed pretty much around gravity. So, I mean, I'm not saying that my north to south direction magnet free fall is the results are as accurate as they should be to match like theory and actual results, but I think it's enough to show that the effect is there.
But please, I think do a thorough analysis of those fields and interactions, because I mean, again, it'll save you a lot of trouble, and it will guide you in the right direction as well.
Okay.
Awesome. Okay. And let me see. Curtis, go for it, sir.
Yeah. So, are you having something spinning in the air?
No. I mean, sometimes it rotates and tumbles, because it's not falling vertically as well as it should, but
Okay. And so you're saying you're getting a difference depending on the orientation of the magnets.
yep.
Do you have a picture of the device that you can share that you dropped?
Well, it was in the presentation, the green objects. I mean,
Yeah.
that's basically it.
Okay.
There's two of those neodymiums, so it takes up about 2 inches thickness, 2-inch diameter, and then the
I
rest is
see.
just foam encasement, and then on the back end, about 20 millimeter thick, where the circuit boards are all in a foam and soldered together. And then at the very tail end is the new IMU that's in the back there.
And you've taken into account the local electromagnetic fields that you might be in?
No.
Okay.
I just did free fall drops in my living room, up at the ceiling to down. And when I did that in Mark 1, like I said, nothing interesting occurred.
I think if you look into, Jim would tell me that there was work done by one of his students, Jim Woodward. One of his students looked into this quite extensively. So you might want to find out what those papers are.
Okay.
Because that's always advantageous to see what other people have done.
Yep.
And you might see where they might have figured something out that you might not find. So I don't know, Jim, are you there? I think he was here.
Yeah, I think he
Yeah,
is.
yeah, we'll see if he pops in.
Okay.
My video's not working for some reason, and I can't figure out what it is.
Ah, okay. Well, we'll come back to that in another time. But yeah, did you have something you wanted to add, Jim, or should we?
Yeah, Tom Hood was the student who did the work
Okay.
back in 1999, I think it was, maybe 2000. Boyd was alive at the time and told us about the magnetropping experiments he had done in the cafeteria at Lockheed's Lightspeed Corps operation. And Tom was so flamed out by it, he went and built some elaborate apparatus and all that. And he found that there was no effect whatsoever on the orientation of the magnets and all that.
Huh.
I don't think he ever published anything on it, but you know, there's a serious negative result to be taken into consideration. I'll try and get a hold of Tom and see if he's got anything on it. He may have it on his website, which used to be called bluefire.org. But be careful. Is
Jim,
all I've
thank
got.
you. Yes, thank you.
Okay.
Yeah, I think I mean, things like this, right? These stories get out there and they circulate around. And so I think it's wonderful to be able to retest them, you know. And then, so Robert, I'm like a big fan of the work you're doing, because you're taking something that everybody has heard of and you're like, hey, let's do this, you know, you're actually taking action on it.
Yeah, I've only come across about a half a dozen people who have done this. That's been published anyway. So.
Yeah. Yeah. And it's good to document, man. So
And
thank
with Boyd Bushman, I can't help but wonder, you know, given he was probably had access to classified programs, that maybe he just, you know, said that the repulsively coupled one falls slower than the control, and in reality out of control and then a normal dipole magnet, and he was dropping the one with the moving north to south. Now it's hitting the ground first, and it was his way of trying to encourage other people to look into it extensively to see, so they could discern the truth, because he obviously wouldn't be able to tell if, you know, if he had been a part of classified programs with that inertia reduction in that respect.
So let me go to Robert. Robert, you have your hand up, sir. Oh, here. There we go.
Can you hear me?
Yeah, welcome back.
Okay. Yeah, I've been doing some experiments with macroscopic effects that can be seen from the Casimir force.
Okay.
I think you got a call from Mark Sokol early in August. I was at his place in New Jersey, and I was showing him this here device, what I call a force. It's a one-layer force cell, and basically it consists.
Okay. Do you want me to? Should I spotlight? Do you want to do kind of a presentation on it then?
I don't want to do a full presentation.
Oh no, just kind of an ad hoc. I mean, I'm just wondering. So maybe we'll stop taking questions for Robert then, and if you want to show us more about it.
Yeah, I wanted to avoid sharing screen because it's such a pain in the neck.
Oh no, you don't have to. I'll just spotlight.
So I was just gonna throw stuff up so you could see it from my video here.
There we go. Yeah.
Okay. So I can see what I'm doing here. Let's see what this looks like. Okay. The dark layer on the top there, that's a grating on the bottom, the lighter color. Oh, let's see. Oh, that's got it backwards. The silverized one on the bottom is actually the grating, and the other one on the top is actually a mirror. Now the grating has been processed. It's a diffraction grating, just something you can buy commercially. Got it from Thor Labs. 1,200 lines per millimeter. And first part of the process, you remove the aluminum on the grating, and then I re-illuminize half of it. Right, so half of the grating is aluminized, half of the groove. And now I put this mirror on top, so it forms a whole series of little wedges. Okay, and there's a theory that has been published by a number of people going back to 1979, I believe, Deutsch and Candelas, that shows that when you have this Casimir wedge, there's a force along the direction of the angle bisector. Okay, and so the question is, does that produce an external force? Or that was my original question. And so I put this device together and measured it in a scale that can measure 1/10 of a milligram. And lo and behold, there are force differences between when you have it up and when you have it down. All right, there's a difference in the measurement, and I did this for a number of such combinations. Here's one I call GM3. I don't know if you can. There it is. Is it upside down? No. Okay. Looks like it's going the wrong way though. But at any rate, you can see it starts up here, goes down, goes up, goes down, goes up, and there's a net force. Looks like if you average it, it looks like there's actually a net force here going across here. So I did it for a number of them, and basically the strange thing here is that the force difference depends upon the orientation of this device in the scale. And so you have it pointing one way, you get one force difference. If you point it a little bit another way, you get a different one. If you put it in another way, you get a different force difference. And so you have this orientation problem. Haven't figured it out. And you get different orientation patterns depending upon which one of these devices you put in the scale. All right, that's part of it. Next thing I did, I'm more recently working on a float experiment, and the float device looks something like this. It's just a kitty litter box with some plexiglass on top, and I've put these aluminum baffles in it. And in the center, there is one of these plates you get from frozen foods. And in that, I put some of these some of these force cells. Here's one here, and here's another one over here, and see if it rotates. And in fact, it does rotate, but it rotates in a weird sort of way. Here's one result. You start it, let's see where it says start, stop, it's backwards. So it starts over here, and it starts off slowly. It accelerates, goes kind of fast over here, and then stops over here. On the other hand, if you start the grading over down here, let's see. Oh no, this is the opposite one. This is the GM5. This is the GM3. Over here on the bottom, where it start? This is all backwards. Looks like this is start. Yeah, I don't know how to get around that. But at any rate, now this is GM3 stop, GM3 start, GM3 start is down there. Okay, so now it starts down here, and now it's going, well, it looks like counterclockwise here. On the top one, it was going clockwise. In other words, it's going the opposite direction. And so it has a start location and a stop location. And it's oriented in a particular direction. if I rotate the kitty litter box and do the same thing, the orientation is absolute.
Okay.
It seems to be oriented perpendicular to the Earth's magnetic field. Although when I tried to see if any of my devices magnetized, it was mostly negative. You know, there was a slight magnetized one of these paper clamps was slightly magnetized. However, the force there is so small, you know, it barely moved a paper clip, and the paper clip is like 250 times weaker, or you know, the weight is less by factor 250 of this stuff that I have floating in the water there. So I'm discounting. It's not directly a magnetic, whatever it is. It's not a magnetic thing that's going on here. So I don't know what it's orienting with. When I did the orientation thing with the in the scale, that was oriented with the scale. You know, if I move the scale around, the orientation pattern moved with the scale. On the other hand, when I did the float experiment, the orientation was absolute. And that's sort of where I am right now. I'm trying to see if I put some sort of acoustical stimulation, whether I'll get some different results. And I think I will. And if I do, if I get something that looks like an actual thrust, that's a paper, you know. That's a very interesting result.
Yeah. I think this is really exciting. I would say keep testing it, keep writing it up, keep giving us updates on this, you know?
Yeah. The problem is it takes a long time to do this because it's like each point is like 50 weighings. So it's like more than an hour's worth of work just to get one point. So it takes a long time.
Is there a way that you can streamline your experiments? And that's something that I've looked at. I mean, again, I'm over at Falcon Space today, and you know, I think that's something that everybody kind of struggles with, right? Is like, how do you minimize the number of variables, and you know, and then minimize the number of tests that you have to do because of that?
Yeah, I don't know. The problem is when I put these extra variables in, I get new phenomenality. You know, it won't go away. I'm trying to get enough stuff so I get a pattern and things start to converge. Right now, things are still diverging.
Okay. Okay. Awesome. Well, does anybody have questions? And Rick, go for it, sir.
Oh, hello, Robert.
Yes.
Your first experiment, I've done experiments with magnets and metal plates. And I find that the gravity field, electric field, and magnetic field of the Earth are all oriented different. And I find that increasing or decreasing the surface area can affect everything. And if you put those like triangle shapes, you're increasing surface area, you might get a bigger charge. You move it around with the different magnetic field of the Earth, and it'll affect everything. So, along with the electric field and the gravity field, and when you flip it over, it may be more like a capacitor, and you'll have a positive on bottom, negative on top, or vice versa. So that's why one increases, one decreases. Just my opinion.
Well, this is a Casimir effect.
Yes,
And
Casimir effects have to do with charges also on the plates.
Yes, there is a force perpendicular to the plates.
Yeah. When you have the two plates, you're going to get virtual particles. You're going to get electrons, and it's going to charge up the plates. And that's what some of that has to do with the force on the Casimir effect, because I've read about it. So just an observation.
Okay, thanks.
All right. That's all.
Yeah, and Rick, thank you, sir. Okay, so let me see. Henry, you had your hand up. Go for it, sir.
I'm also wondering, are you logging uh, time of day, month, etc.? Because you might also be getting some confounding factors with when you're running the experiment, where the Earth is in its orbit. Ugly things like that could be occurring.
That could be. I do keep track of the day and the date. Time I haven't been so particular about because it takes so long to do a single run. So, I mean, temperature changes during the time that I'm doing a run is probably a lot more important than any other thing. Temperature is the scale is very temperature sensitive.
But my point is that because you have all of this divergent behavior, everything that you can collect data wise, more is better. You can always throw it away. You can't collect it when after the fact.
True. And I try to collect as much stuff as I can. So I do have, the date and all that kind of stuff.
Okay.
Awesome. Okay. Well, so yeah. Who would like to present next? If Robert? Okay, go for it. Oops, I'm asking you to unmute, but it looks like it's not. Okay, Robert, you're muted still, sir.
Yeah.
There we go.
Am I on now?
Yes.
Okay, I made it.
What do you got for us, sir?
Yeah, I'm a new guy to the group, but I did some experiments that relate to the first when you're starting to use magnets. I did some experiments using the Cavendish experiment, and of course, that's on a pendulum that comes towards the mass on both sides. You have a pendulum with two weights suspended and then two stationary weights on opposite sides. And you get pretty incredible results. I just use 3-inch steel cylinders, and you can kind of see it. I can put this up as the setup.
Yeah, that looks great. That looks great.
Okay, it's in my garage in Florida. Now, can you kind of see what's going on there? And instead of just using the straight Cavendish, I bought a whole bunch of magnets and tried to work with those to see if I could see some changes. Now, I think by doing this in a horizontal, you take out gravity and you might take out electromagnetism forces from the Earth, just like Cavendish did when he figured out what Newton's constant was. So in doing this, there is a lot of errors that are a problem in that the time you try to start this and get momentum out of that pendulum and all that. But my first time, I used carbon steel cylinders, and then I had 3-inch magnets and put them in line and around it to try to push electrons in and out of their molecules. And then I thought, well, carbon steel, maybe it isn't so good to use a ferrous metal. So I went and had to buy a whole bunch of copper, at 3-inch diameter. And basically, when I started, I did it with no magnets. And you'd be surprised at how you can see gravity working with the Cavendish setup. I could set it apart like the movable weights. I set 10 inches from the face of the opposing stationary weights. And it would only take about maybe 11 seconds. You could see it just taking over and accelerating towards those stationary plates, and you can time it. And that was the indication of if I was getting a change or not. Then I took magnets and lined those up, and of course you can use the positive or negatives and get different effects. The problem I had was that I thought I saw a trend in doing this, but I have so many errors that I really couldn't count on it. But I think it's a good test mechanism for testing out what you might want to do, what you might want to find out, how it might be affecting gravity. I used the copper to have the non-ferrous because I was concerned that I'm magnetizing the metals. And I got basically the same results. But I will say that I thought I saw a trend that I could increase gravity using magnets on my setup.
Okay, awesome. And let me see, Phil, did you have a question for Robert?
Yeah, well, not a question, but just an observation that maybe you might want to check, because the Cavendish experiment, it's really a flipping point in research, because I did the Cavendish experiment myself based on the the guy from the Phil Forward research, forgot his name, but I did the Cavendish experiment using light, and apparently the energy potential from light is also attracting a metal rod, and that would mean that electromagnetism is also responsible for gravity. So any form of energy potential, either gravito-electromagnetic or electromagnetic, can induce a force or an acceleration. So you might want to check that out also, Robert. If I'm just trying to give ideas you might want to check out here, because I think it's a very important experiment, the Cavendish experiment.
Yeah, it's a good basis to go by, since Cavendish discovered it and he could measure gravity. But I was surprised just how quickly you can cover 10 inches by just releasing it and letting the pendulum swing. And you see gravity working on horizontal towards masses that are stationary. It's a very, I say, accurate experiment to define gravity, especially if you're manipulating, you want to manipulate the masses in some way, the stationary
Exactly,
masses.
Yeah, I wish I had a big vacuum chamber to replicate the experiment, but
Yeah, I didn't have a vacuum chamber. That was part of my problem. And of course, with the magnets, as soon as they heat up, everything kind of goes haywire. So that was another really big problem in doing my experiment that led to errors. And I haven't been able to get back to it to try to get a better lab or something. But if anybody has a lab that can eliminate these errors, I think there's something to be found there.
Yeah, it's a very important flipping point experiment there. It can change everything, and it would link, like I was saying, it would link the electromagnetism with gravito-electromagnetism. So problem solved. Let's turn the page.
Sure.
And but yeah, keep going, and I think I think Mark is has wanted to do the experiment with the vacuum chamber at some point, but that's what the guy from Felford Research said. But I don't know if it's gonna do it today or later down the year.
You know, I think Mark does have several experiments planned for today, so I'll touch base with him in a moment and just see what he's got planned. Because again, he's got a bunch of folks over at the Falcon Space Lab, and you know, I'm really happy that I was able to visit. So, Dennis, go for
Yeah.
it.
There I am. So, hi, everybody. And by the way,
Welcome
Tim,
back.
congratulations on your anniversary.
Oh,
By the way, so I've participated with APEC for the last probably 6 or 8 months. As a quick review, I am a principal investigator for an NSF Phase 1 study that completed at the end of October last month. I'm proposing into Phase 2, and it is you know, the research is for a propellantless drive using circulating working fluids. And Tim, I do want to get on your agenda in the next couple of months.
okay.
I have a hard Phase 2 proposal deadline in March of next year.
Hmm.
And I'm working towards that right now. But I did want to, and the reason I got on is I want to share real quickly, as part of my Phase 2 effort, I have to write a commercialization plan. So I was reaching out to vendors for pulse width modulators to drive electric motors. So my experiment runs with electric ducted fans moving working fluid inside of a torus. That's the model, the experiment that I used in Phase 1, and I'll continue into Phase 2 with that. So I was looking for pulse width modulators because I'm using hobby grade parts right now. So I sent an email out to a company, Oberon Space Technologies in Hawthorne, Minnesota. Well, it could be Michigan, but anyway, I said, "Hey, you guys, can you cost out Hall thrusters and your pulse width modulators for that?" And this is what I want to share with the group: is they got back to me. They said, "Thank you for your interest in Oberon, but we'll pass." I checked with the CEO. This is the VP of Business Development, and he says, "We don't want to get associated with some companies preaching propellantless thrusters."
Hmm.
And I thought, yeah, I mean, you guys are making, APEC it got the word out, and they're saying, I mean, so anyway, they're listening. The bottom line is that the word is out. Propellantless thrusters are in the lab being developed, and my intent in Phase 2 is to move to a TRL6, which is the point where you basically qualify your hardware for commercialization. And I've talked with NASA, DoD, and most recently with commercial companies. They're all the same, TRL6, and we're interested. So in other words, get your hardware out, concept demonstration at TRL3, and then TRL6 in a vacuum chamber, and they will start listening to you as for potential applications.
Yeah.
So again, I'm going to close. That was just an announcement I wanted to share with you guys, and I got to run.
Awesome. Well, Dennis, thank you. And I'm sorry that you had trouble getting parts. It sounds like I think it's completely irrational for there to be a stigma, but it sounds like there's still a stigma.
Yes.
So.
Oh, no, there is. And
Yeah.
So prior to doing the NSF Phase 1, my concept was really a hard sell. It was only after I finished all my experimentation and had hard data that I could pitch to, like I said, NASA, DoD, and everybody that the difficulty of delivering a message of experimental results is kind of, I'm moving past that. It's no longer a really hard sell, and I just deliver the message, and I know what the feedback's going to be. Get to TRL6, and we'll listen. And so I'm good with that.
Okay.
Tell you the truth.
Yeah.
Yeah.
Yeah. And again, I would say keep pushing forward with it, right?
Oh yeah, no, your organization really is
You know what?
making
Here's Mark right now. So Mark, are you
Yeah.
gonna do some demos for us today?
I'm actually going to run an experiment in the other room.
Can you do your phone and put it on the?
The guy doesn't want us to video it.
Oh, okay, okay.
It's
Oh, thanks, Tim.
Dennis,
we have some top secret stuff going on here.
Dennis, there is a part, an SG3524 chip. It has a very wide range for doing pulse width modulation. 16-pin dip chip.
Let me see. I think Dennis disappeared from my screen. I wonder. Okay.
Well,
Did he might have dropped.
he might have dropped.
He might have
Oh, well.
dropped. Yeah, I don't see him on my screen now. Okay. Okay, well, I'm sure he'll be back on pretty quick. So let me see. You know, I should ask Jim, you had an update. Do you want to do an update for us? Jim Woodward?
I've got a problem. Wait a second. Oh, I'm not muted. Okay. I'm having trouble with my video. Let me see if I can share my screen.
Okay. Yeah, Curtis messaged me earlier and said that you had an update that you wanted to share, so that's why I'm asking.
Okay, can you see my screen?
Yeah, that's your Zoom window. It looks like it's sharing
Yeah,
your.
I know. How do I get out of my Zoom window?
Oh, okay. Here, let me stop. I'll stop your sharing. Okay.
Okay.
Yeah, I should apologize to everybody for being a little spacey today too.
I'll tell you what. Let me check back in and see if I think Zoom is what the problem is with my video. Okay, because if I turn my video on, that's what you get. No, that's video off. Wait a second.
I had a similar problem getting my video. There was a dialog box on the bottom that said this session is being recorded, and we certainly saw it. When I clicked it, it went away, and then my video came on. So make sure there's no dialog box, extraneous dialog box on your screen.
I can't.
You might have a pop under. So instead of it being a pop-up and being straightforward, it's hidden behind another window.
Yeah. Well, and Jim, I think you can share if it's just like a PowerPoint update. If you try sharing again, if you have that PowerPoint open, you should be able to share
Well,
it.
it's not PowerPoint, but it's
or a PDF or something.
Like okay, share.
Yeah.
You got my Zoom window.
Okay. Yeah. It's so right now it's just sharing. It's sharing everything. So it's maybe the.
Yeah, I need to get rid of the Zoom window. It's what I got. It's supposed to show my video cam, and it's not. Nuts. Let's see. I'm going to drop out and try signing back in.
Okay. Okay. Well, yeah. Give that a try, and then when you're back. So now,
wait, I got rid of it.
Yeah. Now it's showing your screen.
Now it's got my screen. Okay.
So if you go and play that video, yeah. So what you should be able to do is share your screen and just maximize that video.
I'm sharing my screen and I'm going to go get. Okay. 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 What I got is some run results. The devices we're using are standard ones.
Okay.
Stack of
And I'm going to run
crystals.
for just a moment. I'll be right back. I need to use the restroom. So.
Okay. All right. Anyway, for everyone else, now that Tim's going to the bathroom. The run results are shown here. These are devices with 19 millimeter diameter PZT stack clamped between an aluminum cap and a brass reaction mass. This is Curtis's configuration. He's trying to see whether or not what we have is a little stick slip motor. so that when you run the stack with a sawtooth waveform that's 10% symmetry, that is, say, steep on the uptake and slow on the downtake, and 90 degrees symmetry, which is slow on the uptake and sharp on the downtake, if it reverses the direction of the motion of the device. Okay, and what these are is run results for, this one is 10 degrees, and that's what you can see there. And when we go to 90 degrees, the next one, that's what you get. These are obviously different because of the different symmetries, but if you take a look at this blue uptake here, that's resonance transit in the device. And what you'll see is the positive going pulses corresponds to the resonance transit. And the same is true for the 10 degrees spike, which means that no, we're not running a small standard piezoelectric motor, that there's something else going on. Okay, to explore what else is going on, you do this, which is complete symmetry. That's a 50% symmetry waveform, which is an exact sawtooth. Okay, and what you get is this, again, the positive going spike at the resonance transit. And what you do then is ask another question, because we know the system is, what do you get when you just do a sine wave? And that's the answer. So a symmetric sawtooth and a sine wave give essentially the same result. The sine actually gives a slightly larger result in this case. So we're instrumented to do a bunch of stuff. We do run movies and so on. We have picoscopes hooked up to sensors that record both the waveform of the voltage signal being delivered to the device and the waveforms of the current signal. And we have mechanical accelerometer built into the stacks, so you can get that too. And then we're going to go past that one. These are some done on the 7th, which are similar sorts of things. But this is what Michelle put together for us from the run movies, which record all of this. This is a 10% waveform here. And this is the fast Fourier transform of this red trace, which is the current in the device. And as you can see at resonance transit, you get a fairly large green pulse here, which is the strain gauge or accelerometer, as you choose to call it. Okay, the other traces are blue, which is this one here. That's the voltage in the device. Red is the current, and the other one is a real-time computation of the dissipated power, okay, which is of much interest. That's what happens when you use a 90% sawtooth. Okay, so that's 90, and this is 10, and they're both producing the same sort of effect, but with different amplitudes. This is the 50% wave, and you see there's a very large mechanical excursion in this case. This waveforms are more nearly sine, but there's still a very strong second harmonic presence in the signal, which is the thing that enables this device. And that's a simple sine wave, okay, which is clearly nearly a simple sine wave, but nonetheless, it has this strong second harmonic presence. That's due to an isolation and step-up transformer in the power circuit that works as part of an LRC type of circuit with the capacitance. And that's the reason why you see any mechanical effect worth producing at all. Okay. So what I wanted to do, we're at the end that way we go this. Okay. Okay. What I wanted to say is what we are doing is we are eliminating things that Curtis can think of that might be responsible for the signals other than the hypothesis, which has been tested now for many years, which is that the first harmonic produces a in the inertial mass of the PZT stack, and the second harmonic acting on it with the correct phase produces a thrust by pushing on the stack when it is more massive and pulling back on the stack when it's less massive, which is something that allows you to couple to the gravitational field of the universe, which is supposedly responsible for the origin of inertia, which is a fundamental physical principle, and Curtis likes fundamental physical principles. What our experiment seems to show is, yes, indeed, that such an effect is present, and that with a seriously upgraded experiment, thanks to Curtis and with some help from Michelle on interpreting the results and computing stuff and things like that, we're moving forward slowly, but we've got these as results at this point to show that there is a real effect present. Curtis, do you have anything you'd like to add? Curtis?
No, I think you covered it well, Jim. Thank you.
Okay.
Awesome.
All right.
Well, Jim, thank you. Do you want me to stop your screen share?
Yeah, go ahead.
Okay. And then I know you guys are working on the pump thing. I called Curtis last week, and so I know you guys are coordinating with Drew on that. And that's there was a hurricane in between then and now, so
yes,
things got a little slow, but I know that's something that he's working on. So okay, yeah, good deal. Well, I'm glad everything's moving forward. Drew, do you have any updates for us?
Yes. Can you hear me?
Yeah, go for it, sir.
Okay. First of all, I just got an email from Mark that says they have a spinner up and spinning at his little party. And I'm pretty sure that that's either our tech or something real close to our tech. So super exciting on that. The video he sent was amazing. So I hope he pings in and shows it off or something.
So the one that he has that I'm aware of right now is a fellow named Alexander from Portugal who came to visit the lab, and to me it looks fairly similar. It's definitely a different build than yours. It's kind of a tube shape with something in the middle, and he was saying that it's apparently there's something else very different that he's doing, because I said, is that standard B-field Brown? And he said, no, it's different. There's different mechanism at work, but we didn't have time to really get into it. So in his case,
yeah, he's calling it a Campbell thruster or something.
Could be.
So anyhow, it's very exciting. By any other name, that's the same basic technology as ours. We had things that looked just like that spinning years ago.
Yours is more mass.
Awesome.
Yours is more compact. Yours is more.
Yes.
Yeah.
Well, that's like a super old version of ours from a few years ago.
Yeah.
But other than that, the updates are all kind of working in the shop stuff. For reasons unknown to me, we got a thruster up to 2 millinewtons. That's 10 square inches of thrust surface, weighed 360 grams. That's like 360 milligrams, and operates. It's I don't know. It's insane. The stupid thing was putting out 2 milligrams of thrust with full off, so we can like throw the switch and come up to thrust and turn it off, and goes right back to zero. It's the first time I've ever seen that happen. So that's pretty exciting news. We're going to scale that up and probably go up to a 20 millinewton thruster, because I mean that's 2 millinewtons. So we'll probably for this week we'll probably scale that up to a 20 millinewton. I decided to bring my 68-inch vacuum chamber online. So I'm going to get it to where I can go high vacuum in it. I'm going to mount I got 4 spare turbos. I'm going to mount 4 turbos on it, and we're going to weld up all the plates and holes and everything, and try and get that thing down to 10 to the minus 6. So that's kind of available to the gang if anybody wants to try out some experimentation. Obviously, it's not portable. The thing is the size of a par, but 68 inches in diameter, about 65 inches deep, full empty, though that the whole volume will be 10 to the minus 6 with high voltage pass-throughs and data communication and stuff. Anyhow, if anybody wants to try out some crazy thing and I can't afford NASA or somebody else's chamber, you're certainly welcome to show up here in sunny Florida and toss your toy in there and play with that. I should be online in about a month.
Awesome. Well, Drew, thank you. And
got it.
Yeah, I should ask you and anybody else if for things like that, drop your email into chat or contact info of some kind so that people can reach you. And that way, if it's in chat, it won't end up on the open internet, right? Because this is Zoom. So that makes it pretty safe.
Okay. Can do.
Awesome. Rick had a question. I see Rick's raising his hands. Go for it, sir.
This is for Jim Woodward.
Oh, okay.
We're always watching Jarod do arts parts with the nanoparticles and the layers. So what I might suggest for Jim and Curtis is to make a metamaterial with layers of brass, with epoxy gluing them, or maybe use brass particles in an epoxy and see, because I always find gravity effects are a lot to do with surface area. So it's just a suggestion.
Thanks, Rick. Okay, well, so let me see. Does anybody else have anything to share?
Yeah, I started a band with 5 other members, and near the end, if people would like to hear it, it's about like a minute and a half long. It's
Okay, well, if it's a minute and a half, Jay, do you want to play it now? Play it for us.
Sure.
Maybe do a screen share. Remember to share audio. There we go. Okay, it looks like it started screen. Okay, perfect.
Technology is how you use it. Divergent disturbance, we gotta choose it. Yo, make it vibrate. Specific frequencies resonate, make it great. Gotta make the people see the technology. Start with fire, uncloak, unprovoke, and let the people hire to make us program. Otherwise, good interest, these people damn. They invest into disinformation, official interference, low vibration. In the real sense, through the dimensions, we rise, awareness ascension, till we get wise to the technology. It's how you use it, divergent disturbance, we gotta choose it, Yoka's technology. With outside forces, Schauberger told me to flow with the courses as the way of guide. We resonate them all, narrow too wide, filter noise to call up the energy from source to a higher vibe, amplify the force so we can ride this energy state. Like a laser beam, resonate, make it great, gotta make the people see the technology. Starts with fire.
That's awesome. That is awesome, man. Yeah, look at that. An audio visual elements.
Yeah. So I'm on vocals, of course, and then we have a guitarist, a drummer, and we're gonna bring on a kazooist and a saxophonist, and also a person with a loop deck. So yeah. Thank you, Schauberger Flow. Yeah.
Yeah, there you go. There you go. Guys, give me just a second. I'm gonna mute myself out here real quick and go see if Mark is ready for stuff.
Well, that looks like Mark's lab over there on David Chester's feed. And it looks like he has pretty much half of APEC in his lab. There must be a heck of a party going on today.
Okay, sorry about that, guys. So I am over at Falcon Space. Mark suggested if I can do this without destroying the laptop, that I pick the laptop up, carry it around, and show you guys what's going on. So I'm gonna do that. Let me unplug from power, and I will pick it up. And here, let me spotlight. Okay, so I'm gonna disappear for a moment here. There we go. Okay.
That motor is much smaller. Than
Yeah, so we're over at Falcon Space. So I've got the gang.
We're working hard.
Yep. So we've got one thing we have there is test chamber. You know what? I don't want to open that quite yet. Hey, Jarod.
Hey.
Yeah, so there's Brian Kelly.
Hello.
Yeah, Kurt Zeller and Jarod. And that was the chamber that I was just opening. And so they're doing some testing in there. I didn't want to disrupt the testing. That's lab equipment there, signal generators and stuff. This is Mark's dynamic nuclear polarization system. Charlie is here.
I've got
Charles
Campbell
Crawford.
Ruster here sitting.
Okay, we actually have some more testing going on in there.
Now we have another thruster here.
Oh, well, there we go. Okay, so that's in air, right? But we're going to test that in vacuum later.
All right, and check this out. We got the mercury vortex engine for Wolfer next. I'm going to power this up for you guys for a second.
That's the mercury vortex engine?
No, this is the metal vortex engine. Liquid metal vortex engine. That's what it's called. And we're using these cool little nifty motors.
Okay.
And we're going to spin this up right now. You guys ready? So, yeah, this motor is actually out of an electric skateboard, and that's forcing the mercury to rotate around, and it's supposed to create a thrust in this direction. So we're going to set up a test rig.
Put that on a skateboard?
That's probably a good idea to put it on. Yeah, put it on.
Yeah, or do you have something with rollers that rolls easy?
Yep, that's what we need to do. So that's what's happening over here with the mercury vortex engine, and it is complete as promised. Although we'll probably wait a week or two late because I said it would be done in October, but we had to do some redesigns.
That's awesome. That is awesome. Look at that. Okay, well, do you want to give us a tour?
Yes. You want to turn on the spin lathe and show everyone what you're doing? We have Yoav here, and he's going to show everyone how to make a spin lathe. And this is actually for the outer hull of a flying saucer or mini saucer that we're going to be building here at Falcon Space. So it's a wave guide.
So yeah, there's the spin lathe. We're making discs. Wow, look at that.
And we need discs because you got to have a double hull of the craft in order to fit microwaves inside.
Awesome. Thank you. Okay. And there's Michael Perrone. Okay.
Yeah, we got a replication of Charles Bueller's work here. This is Kapton, and each of the thruster plates is inside the Kapton because the 3D printing plastic probably has some trace magnesium chloride or other polymerizing agents in it. So it can't at high voltage the 3D printed plastic effectively conducts. So you have to keep the plates isolated with Kapton tape when you're making it for use in vacuum. And yeah, you separate it in the Z-axis using Delrin rods, which absorbs very little water. And then the rest of this, we just off-gas it in a roughing vacuum for a few days. And I'm just doing the final assembly before testing. And you can see it just takes a touch and it goes around. There's some stuff for Drew that I was promised I wouldn't show, so I'm not going to flip it around. But yeah, I mean,
there you go. Yeah.
But yeah, I mean, making one of these in vacuum is not an easy task. But we have a device for use in atmosphere. So these are hermetically sealed based on the stuff that Drew showed off during Tim Venture's interview with him a while back. So this whole setup is pretty much precisely what Drew was showing off. And it doesn't have a force measurement thing. It just has a balance. So we made these balances. And so for both of these units, it just has a tungsten raw needle in the center. And then you have a pool for liquid gallium indium. And so there's no stiction whatsoever. And there's just there is a small plastic bushing. And that bushing is the only place where stiction can occur. And if it's well balanced, then you'll minimize the friction on that surface. And it's only like the tungsten rod's only 2 millimeters. 2 millimeters across. So it's the torque exerted by that stiction is tiny. So this thing also like all of the high voltage lines are covered in ground. And this one's covered in Corona dope, but I haven't had time to cover this one in Corona dope, and I won't because we're putting this in vacuum in like a few minutes. But if we want to redo this experiment with everything done perfect, I would cover this high voltage line here in Corona dope. And this just prevents arcing. But this is a Corona dope around the ground, so we're really like going all out here. All of these smaller wires, this is 12 volts, so not much. These are ground. These are all ground. So they don't really need insulation if everything's working properly. If things are not working properly, we might want to just put high voltage putty around all of those or Corona dope as well, just to like get everything, working right, or beyond any shadow of a doubt. So, and then this whole apparatus, just like that, will go under a aluminum foil shroud, which will serve as a ground enclosure around the whole thing so that electrostatically it's minimally interacting with its environment. We can even put it in the Faraday cage where it's a secondary ground around that. So we know that it's at the same potential instead of like stuck in the room having a static charge.
Yeah.
Hopefully.
And then this, I think this one, it's important again to point out that Drew and Charlie have a lot of intellectual property. And so you're not infringing on that in case.
Yeah, so there's certain aspects of this one that they would like as their intellectual property. There's actually a few improvements to their design that I found while I was building
Okay.
this that they'll be interested to hear about maybe. And then this one was I mean they already talked to you about this in a video.
Yeah.
So that we're gonna see it. We should be able to just open source this. Like all the 3D printed parts can go on like what's the Hackaday and GitHub and all the other instructions as well.
For the public stuff. Yeah. I just, again, I want to be very, very super sensitive to NDAs and intellectual property and anything like that. So
So this one here, yeah, this is I mean it's a very simple build relatively speaking. So anyone could do this. Putting this in vacuum, there's so much extra stuff that like this model is like 3 years of extra iteration by Drew and his team of improvements on that model. Like to go from in air testing to in vacuum testing, you have to redesign everything pretty much.
Okay.
So it's there's a lot that goes into this. But if anyone wants to prove it to themselves, this one works in air. These are all ground. You can cover it in silicone. And then inside that is coaxial. I've put copper tape around that, so all of that's ground. Then the only area where there's high voltage is right here, and then you have the external ground around all of that. And then these foam blocks are hermetically sealed with silicone, so there's no ions coming out of that unless they're at high enough voltages that they can tunnel through, maybe. But yeah, these blocks are hermetically sealed. So with this sort of device, you should be able to get a demonstration of this in your own house if you want.
Awesome. Well, Michael, thank you, sir. Thank you. Okay. And we'll head back. Hey guys, you want to show us what you're working on?
Yeah, so we're trying to replicate the John Brandenburg experimental setup here. So at the end of the day, John Brandenburg is claiming you can just take a 3-phase motor, power it up, and get anti-gravity. So we'll give it a shot. We're playing with a couple modifications as well, but not looking so great so far, but still inconclusive, I'd say. We're still collecting more data, doing some more experimentation, so we'll see how it goes. But it's not really too complicated. It's just a 3-phase motor with the rotor taken out. We were just using the oscilloscope to power it up and just verify the frequency, and weren't seeing what we were expecting on the scope. So now we're going to put the rotor back in and make sure our scope is working properly and then hook it up again. So, I mean, not much more to say besides that.
Awesome. Awesome. Well, David, thank you. Mike, thank you as well. Yeah, we have a lot of stuff going on. Oh,
no, I think I got it.
Jarod, you want to walk the APEC people through? Okay.
So right now you're going to want to see.
Okay. I don't know if I'm holding this. Yeah, there we go.
So right now, this is a metallurgical microscope. This microscope allows us to see some really interesting features on the piece of the Roswell material, Art's parts, that we haven't seen before. So let's see if I can have Tim come around to the other side. I have it set up so there's a camera here, so you should be able to see what I'm seeing on the microscope here.
Okay, now I'll tip it a little bit.
Yep, let's see if I can zoom in just a little too, make it easier for people. So there it is. We have a very small sample. This is the minimum amount of zoom. The very interesting thing, though, is that when I zoom way down in on it, here's the next zoom, you can start seeing some morphologies on there. Sorry, multitasking is hard.
And we're probably going to put these up online, right?
Yep.
Yeah.
So the new thing that I found since I've been here is when I get to the maximum zoom, there are some places on here where you start to see these little fibers. They're like 1 micron diameter or less.
There, and I'm not sure if this will show well.
And it won't show up, but if you give me a second, let me pull up a picture on my laptop and I'll share screen for everybody.
Oh, okay. Oh, because you're on.
Because I'm on Zoom on here.
Okay.
So let me share screen. Window.
I will do admit all. Okay, and hopefully it's still.
There we go. So
Perfect.
Over here on the right, you can see we got like a central
spoke here or central hub with all these little spokes coming out. This is the maximum zoom that metallurgical microscope is capable of producing. So the diameter of each one of these being at a micron or less, we're talking really small here. This is not the only image I have of these. I'll show you a couple others here in a second, but the first thing I compare this to, and it's a Rorschach test, you know, everybody sees what they want to see. What I see is I think of these little erasable programmable memories that are like older from the 80s. You use UV light to erase the memory. Anyways, they got all these little like gold legs that are all soldered off of the chips. And that's kind of what I saw when I looked at this. Now, I got a couple other versions of it here. There's the spokes right there again. Now, this is magnesium orthosilicate, which we have sitting here. I was trying to compare the two. This is not max zoom. This is half max zoom. So each of these little fibers, these little white lines of silicate that you see here, are actually really, really wide. Like that's like 5 to 10 microns wide, if not more. So much bigger than these little fibers that I'm seeing. I've taken a couple hours of video here, and as I go through and I do all these different zooms, you can kind of see these white fibers show up. I'll probably end up posting a video here in the next week or two, probably 2 weeks, where I've edited this down so that it's easier for everybody to kind of see like all the fibers that I'm seeing here. Hopefully Wednesday, I'm going to be taking the sample back to get tested again with the scanning electron microscope people and the XRD people. So we might, maybe, we might be able to find out what these little fibers are made of. They might be crystalline formations. They might be fiber optics. They might be nanowires. I mean, there's no way to tell yet. It's all speculation. And I would much rather know from data than speculate all day.
Awesome. Awesome. Well, Jarod, thank you. Okay. Okay. Well, I think that's it. So I'm going to take you guys back in the room here. So it's 4:38. We're going on, let me see. I guess we're going on about an hour and 40 minutes so far. Okay. And okay, perfect. Okay, and who has stuff, guys? Anybody else have stuff to share for us? Okay. And again, it's you guys can unmute yourselves. It's Option Y on Mac or Alt Y on Windows. And I think that's probably everything that we had to run through today. Oh.
Okay. Tim, can you go back and look at that, whatever that blue spinning thing was? The spinning thing in the blue frame?
The spinning thing in the blue frame.
Yeah.
Oh, the Campbell thruster. That was Charlie's. Yeah. Yeah, here. Let me haul it back out. This is probably not the optimal way to do it, but I don't have Zoom on my phone, so.
I had no idea what I was doing.
Okay.
Is that the thing that they had in the vacuum chamber?
Pardon?
Is that the thing they had in the vacuum chamber that Mark sent me the video?
No. But
Where's
they're
that?
gonna put it in.
Okay.
Michael, we're pulling up the vacuum valve for you.
Okay. There you go.
Pulling up the vacuum valve.
Showing by reversing the polarity, let's look at the same direction. Reverse the polarity, same counter rotation. Show again for the APEC keyboard. Oh, remarkable.
Are we looking at a really beautiful ion wind thruster?
It sounds like I'm hearing some ion wind. Yeah, so we need to test that in the vacuum
Sure looks like
chamber.
it's set up to be an ion wind thruster.
Cables are shaking. Yeah. How much current are you putting through them? Not much current, but
I love the red sciencey stuff, man. You're rocking it.
Yeah, I
red-
mean,
the red,
hearing
uh,
some
suit.
hissing, so there definitely could be some ion wind going on there.
Yeah, because it's got all the speed and power of an ion wind thruster.
Yeah.
It sure looks like it's the right design for one. Which are amazing toys, except you put that in a vacuum chamber and it don't do nothing.
Yeah, and so I guess we'll see what happens when we put it in there. So that's here. I'll take you back in the room. Okay. Oops. There we go. Okay. Perfect. How's that? Doing better?
Yeah, that was awesome. Thanks, Tim.
Oh yeah, absolutely. Absolutely. Yeah, they're doing a bunch of tests here. I'm really excited. So Mark wanted to get everything set up for the APEC anniversary. So, we'll see how things go. And then I've got the conference itself. I've got the webinar or the presentations planned out through December. And so I have a bunch of those coming up. And that's all on the Alt Propulsion website. So does anybody else have anything to share for today? Oh, Steve, go for it, sir.
Can you hear me?
Yeah.
Okay. Yeah, I just want to say a few words. Last time I talked about the electronic circuit that can synthesize a terahenry inductor. And so I just want to say a few words about the dipole radiator. I'm constructing a gadolinium silver foil dipole, which basically you need foil because you have to get a relative permeability out of the gadolinium between 15,000 and 20,000. So it's easier to anneal foil than it is something more massive. And so my thought is I'm going to construct a silver gadolinium foil dipole element that's just rolled up. And then I'm going to anneal it after I roll it. And each side of the dipole is 1 inch, so it's a 2-inch dipole. And if you go through Maxwell's equations with that, you'll find that it has a really low phase velocity, which expands the electrical size of it because it's extremely electrical short antenna, which gives it actual credible efficiency for radiating. And I'm setting it up to radiate at 30 millihertz. And I'm hoping to get a power density from that somewhere in milliwatts. So I think I'm very close to getting there. So I just wanted to pass that along.
Oh, awesome. Awesome. Okay. Well, do you think you might be able to do a demo once you've got it there?
Yeah, it's going to take me a couple of months to get it up and running, but I've already synthesized a 5 million Henry inductor, and I can resonate a 1 nanofarad capacitor down to 2 hertz, which is as low as I can measure. The thing about working at 30 millihertz, there's no instrumentation, so you've got to do it all yourself.
Yeah.
Which really slows it down for me. But I've got it now where I think that I can get the terahenry synthesizer working. I'm far enough along with it where I think that one's almost a sure thing. And once I do that, I can resonate with a 0.5 picofarad capacitance on the dipole. And once I eliminate the reactance, then it's just the silver hopefully will give me enough conductivity through the semiconductor of the gadolinium to slow the phase velocity without attenuating my signal too much over 1 inch. So I think it's got a good chance of showing something. So yes, in a few months, I'll be more than happy to share it.
Awesome. Awesome. Okay. Well, thank you, Steve. Yeah. So does anybody else have anything they want to share today? It's about 4:45 Eastern time today. So.
Tim, just give me 1 minute. I'm going to try to video up. So
okay.
Give me a minute.
Oh, okay. Michael, go for it. What do you have?
I just wanted to share this FOIA
Well, let me
response
see
that
if-
came out that I sent. I posted a.
Okay, Drew, can we circle back to you after Michael shows this for you? Okay.
Yeah, I'm just gonna. It just take a minute.
And what I've heard, just so you guys know, November 13th, there is supposed to be some big UAP congressional thing. You
Yeah.
mentioned FOIA, and it brought that to mind. So I guess we're all.
So
gonna-
what I have here is this response to a FOIA request. Defense Intelligence Reference Document 30 March 2010. And this has got a wealth of information, anti-gravity for aerospace applications. And you can see that's FOIA stuff. And then they're covering a lot of the stuff that we talk about all the time.
Does it say who the author was?
That's probably what they redacted. It looks like to me. Yeah, it doesn't have a name.
Okay.
Yeah, so I posted
What
a
if
link.
what if they're using an AI to populate that text? Like they're taking it from all over the internet, everything that we speak, talk about, and disclosing.
Yeah, well, that could be a forensic. That's what you need, what's called a forensic document examiner to authenticate the document. And what they look for is the font type, because doctor documents, they tend to use newer fonts that didn't exist at the time the thing was written. Follow? So the answer is I don't know. But what it does do is it does a pretty good job of looking at it from Newtonian physics. What caught my attention was this page 4 here. I'm going to show.
Yeah,
where
and
this whole section, anti-gravity versus via gravitomagnetic forces, where they talk about Heaviside and Einstein, all these authors that we've talked about, and their description sounds just like what I found in my invention with my device and patents. So I thought it would be a useful thing to share with you guys.
Well, Michael, thank you. And if you're open to it, you might consider uploading that to chat. And then
okay.
Now that I'm looking over there, Todd Desiato and Todd, if you'd like to talk about that, I can bring you on in just a moment. Todd just uploaded one about gravitational time dilation and length contraction from radiative damping in QED without GR. So, but let me go to future craft really quick first, sir.
I'm on mute and I don't have the camera on, dude.
Go in the other room.
Okay.
Okay. There's.
What the hell?
Oops. Okay. Now it looks like he disappeared. Okay. So. Yeah. Okay. So Michael, let me meet you out. And now, Todd, did you want to describe your document? Is Todd still here? I think he's still here. Yeah, he's still here. He doesn't have to, but he did drop the. Yeah, Todd, do you want to describe your document?
Yeah, sure. I uploaded.
You want me to do a screen share for you?
No, I'm just gonna be short.
Well, here, let me put it up anyways, really quick.
All right.
Okay. Oops. Sorry. And now it's not. I just updated my laptop. So.
Okay. This is a new paper I just released, ResearchGate, and essentially it's an extension of my engineering model of quantum gravity, which interprets general relativity and space-time curvature as being radiative damping within matter. So I use the equations and the principles of radiative damping on the length and oscillation frequency of atoms in an thin aluminum rod. And essentially what the paper shows is that just by modifying the Landau-Lifshitz damping factor, you can simulate time dilation and length contraction in terms of the frequency of the atoms and the separation between them in an aluminum rod. That's really all it does. It also, there's an extension paper with it that does a calculation of if gravity were damping using this principle, what the Landau-Lifshitz damping would be from sea level to, I think it was 10,000 meters. So anyway, you're welcome to download it. It's on ResearchGate, not a paywall. So
yeah, well, and Todd, thank you. Well, and it's also in the chat if anybody wants to download it from there. But I'm just scrolling through now so they can kind of get a better idea of the equations and things like that.
Yeah. I'm working on a video to go through the whole thing.
That's wonderful. Well, thank you.
But this is the paper, and hope you'll read it.
Yeah. Well, and again, so I'll stop sharing now. And again, Todd's paper, and I can re-upload this for anybody if they want. Yeah, and I will put that there.
All right, cool.
There we go. I'm just re-uploading it. So yeah, so now you guys, you have that from Todd, and then there should be one from Michael as well. Michael, did you have one to you had one to upload also, right?
Yeah, first I'm just going to send the link.
Okay, there we go.
And then I can.
That's probably not that, sir.
Yeah, I can upload it too.
Okay, well, yeah, and so guys, that was for me. That was probably everything I had today in terms of open mic stuff. Unless you guys do you have discussion stuff? Do you have?
Jim, I got a video.
Yeah. Okay, go for it.
Okay. Gonna take a shot at this. Not sure. Working. I can't tell. Can y'all see a
yeah, there we go.
Screenshot?
Yeah, I see it.
Okay. I decided I'll just do the voiceover. So basically what you see here is about 1,013-1,400 seconds into a test. And the rate at which this thing is making thrust is insane. It's putting on 50 micronewtons of thrust per minute above what it was making the minute before. So I'm about, I'd say about 700 or 800 seconds into this leg of the test. Have it up at 7,500 volts, and this thing's putting out over 1 millinewton of thrust. This is 10 square inches of plastic. So it's insane. When I turned it off, it shot right back down to 0, turned it back on. After another couple of 100 seconds of charging, went right back up to 13 or 14, 1,500. And I ran this thing for another couple of minutes, and it topped out at around 2 millinewtons. So it's crazy. I just wanted to show you that every once in a while, everything works for reasons kind of known, but pretty much not. Anyhow, that's real-time engineering and science and work right there. Just results that don't make any sense until you figure them out.
Drew, that's awesome. That is awesome.
So that's all I got.
So yeah, I'll stop your share now. Okay. Yeah, and does anybody else have anything? We're just about 2 hours in. We could make things short today if you guys want. I'm gonna be wandering around Falcon Space taking photos, so I will have lots of photo and video. And what we're gonna try and do, I was hoping to do some of it live, but Mark has a bunch of folks bringing vacuum chamber stuff, and so we're gonna try and get photos and video of a bunch of different vacuum chamber tests, and it's just crossing the fingers, right, and seeing what produces results and what doesn't. And then I'm just going to try and get photos of the folks as well here, and and then that's when I get back, it'll take me a few days to get those online, but hopefully I'll be able to share those with you guys and you can get value out of that.
day or a week?
Okay, well, why don't we? I think we're at just about the 2 hour mark, so it's pretty short today. But why don't we shut things down for today? So happy birthday!
Where's the cake?
Pardon?
The cake? The cake?
Let me see if I can show you the cake.
The cake should be able to levitate here on its own, you know.
But we don't know what ESC was on that or.
I might get in trouble, but here. Okay.
The motor didn't run after I realized the copper electrodes were slightly hitting the side.
Okay, wing
So I
move your
cut
leg.
There
we go.
Oh, nice.
Happy 4th anniversary
that's something
APEC.
actually can violate conservation I can do now.
Maybe we should do that.
But it's, I mean, now it's kind of pointless.
I'll come back to those photos of that in a minute.
It requires 400 hertz. Yeah. But you can't do that on a lot of it's like.
Okay, so there we go.
Awesome.
Yeah. Well, Phil, why don't we if it's okay, I guess I'll shut things down for tonight. We're gonna be doing testing, so I'm gonna be busy. And you know, I'm just excited to see how everything goes. And so you know, our next one is, I believe it is November 21st. I don't have my calendar up. Or sorry, November 23rd. Let me check really quick. And again, all of this is on the Alt Propulsion website. Oops, there we go. Okay.
Yeah, sorry, I don't have much updates on my end, but it's all I need to get prepared for the.
Well, that's okay. Some of it is
conference
this
in
time of
December.
year. This is kind of I mean, we're all getting, you know, we're starting to move into the holiday season. There's a lot of craziness going on. Some of it is on my end of things. Traveling here, I'm jet lagged as heck, but I'm also okay. So 11/23, November 23rd. In fact, let me open up the Alt Propulsion site, and I'll share that for you guys. Okay, so I will share this. So go to events. So November 23rd, I'll just walk you guys through this really quick. So Lance Williams, I've had to postpone Lance twice. He's had a lot of day job stuff. He's had a lot of commitments that he's been trying to do. And then after that, I'm really excited. Max Fomachov Zamolov, microscopic thermonuclear fusion. And in a sec, I will drop a link into chat on my podcast channel. Max already described what he's doing, so you'll have the essentials there. So I will do that in just a sec. Then Greg Hodgen, if you guys remember Greg is doing his own independent kind of group with emerging propulsion and energy stuff. He is going to come on to talk about the Zero Carbon Institute, formerly the Zephyrin Cochrane Institute, and the lab network, right? And he has like Dr. Chance Glenn and Dr. Jason Casimir, and Jason presented here last month. And so he has a lot of folks that are in his network that hopefully he can give us updates on. Then Eric Ryder is going to be doing a sequel to A Serious Challenge to Quantum Mechanics. Curtis Horn got really excited. Curtis is a giant fan of that. And so I'm really pleased to be able to have Eric back. So that's what's going on for November. We should also have more updates from today's testing. And then in December, okay, so Mikolaj is here today. He's going to be doing a presentation on the vacuum propeller that he's working on. Then the other person is Horst Eckhart, who was presented before, is going to be talking about anti-gravity on the basis of ECE theory, Einstein, Cartan, Evans. This is the theory that Myron Evans was working on. And the thing that excited me about this, there are no guarantees, but there is a fellow named Kellum published something that looks very much like the Graviflyer, and he used ECE theory as the basis for his explanation. And so again, it doesn't necessarily mean anything at all, right? Could just be wishful thinking, but it was interesting to see a theory that supports kind of what the Graviflyer is doing. And so Horst is going to come in and talk about that. Then Remy Cornwall, and I haven't talked to Remy in a long time, so it'd be wonderful to see him again. Microscopic coherent sources of gravitational radiation with forming a stable warp field. And then Harry Sprain, if you guys remember Harry, so Harry had the SID drive. That is basically an inertial propulsion drive, and he's using magnets in it to guide and create some of the inertial propulsion. And so it's kind of an innovative approach to your off-center rotator, right? And he's down in Tampa, Florida. And so Harry is going to be doing a demonstration of that. And at some point, and I may end up going down to see Drew again too. I promised Harry that I would come down to Tampa and try and get video. And so if I'm going to Florida, then I'll have to drop by Drew's lab and bring him some sourdough mix or something. So. Okay, well, yeah, so I think that was everything. I think that's everything for today. Guys, is it okay if we shut things down? Awesome. Okay, well, thank you, everyone. Thank you. 4 amazing years with APEC. And we're moving forward, with experiments, with network, with everybody. It's really, really, really exciting. So thank you.
Happy birthday to you.
Well, happy birthday to all of you as well.
Hello. Tim?
Yeah.
Yeah, I wanted to ask you 2 questions. Or you just displayed the APEC various other videos that you have produced. Where in the world can you find those? I've tried in the past to locate those, but it's not clear how you get to them to view them.
I'll tell you what, Hal. Let me do this before we close things down. I'm going to drop in our YouTube link. And I'm going to drop that right into chat for you, my friend. Oops. There we go. Okay.
Do you have a result, Tim? Do you have a result on the
not yet. Not yet. We're still working on things.
On the motor that David Chester was fooling around with?
Not yet. But I should be able to go out and get some more info in just a bit. So guys, let's close things down. It has been a wonderful, wonderful day, and I look forward to having more results for you, and hopefully you guys have more results for us as well next time around.